G'day! Some 2,000 years ago, Theon of Smyrna knew that if a over b is a fraction that approximates the square root of 2, then replacing it with a plus 2b over a plus b gives a new fraction that's a better approximation to the square root of 2. For example, let's take the bad approximation 1 over 1. This is number 1. That's 1.0. Not a very good approximation to the square root of 2. But to get a better one, replace the denominator with 1 plus 1. That's 2. And the numerator with 1 plus double 1. That's 3. You get 3 halves. 1.5. And yes, 1.5 is indeed a better approximation. To get a better one still, do it again. All right, replace 3 halves with denominator 3 plus 2 is 5, and numerator 3 plus double 2 makes 7, 7 fifths. That's 1.4, and that's a better approximation still. So if you do it again, 7 plus 5 is 12, and 7 plus double 5 is 17. You get 17 twelfths. That's about 1.4167, I believe, on my calculator, and that actually is a better approximation again. Another time, 17 plus 12 is 29, 17 plus 24 is 41, bingo, 41 29ths. If you do that on a calculator, you get something like 1.4137, something like that, which is better again. One more time, 70 for the bottom and 99 for the top. 99 70 is about 1.41428, I believe. Getting better. Again, one more time, you'll get 239 and 169, which is about 1.414201 or something like that. It's getting better and better. You're getting much better approximations to the square root of 2 as you go along this ladder of fractions. In fact, people call this sequence of fractions today Theons Ladder. And it's absolutely beautiful. I'm actually smitten with the numbers that appear on this ladder. I think it's astounding because there's so much wonderful mathematics hidden in the numbers as the numerators, the numbers as the denominators, and in the fractions themselves. And that's what I want to talk about in this video, the magic behind the numbers that appear in Theon's ladder. But to get us going on that magic, we have to look for the structure. And some of the structure you see right away comes from the idea that, well, we're squaring things, we're doing the square roots of things. That's very awkward. So much easier not to deal with square roots, but to square numbers and actually make them whole numbers instead. So maybe squaring all these fractions will help us out. In fact, let me do that. Let me square all the numbers I see as numerators and square all the numbers I see as denominators and see if some structure emerges. I seem to be calling the numerators A, the denominators B. So let's look at the A squareds and the B squareds. That's my notation for numerators and denominators squared, squared. Great. All right, first of all, I see 1 squared is 1. I see a 1 squared is 1. Numerator here is 3, square it makes 9. 2 squared is 4. 7 squared is 49. 5 squared is 25, excuse me. 17 squared is 289. 12 squared is 144. 41 squared, I believe, is 1681. 29 squared, for some reason in my head, is 841. I don't know why. 99 squared, I don't know, but 70 squared is 4900. I bet 99 squared is 9801. Actually, double check me on these ones. I think they're right. I think I've got them correct there. Okay, this one's got me scared. I'm not going to do that one. We'll leave it there. Run out of room. Run out of room, can't possibly do it. All right, okay, so what are we noticing? Is there any structure to be seen in this table of the numerators and denominators squared? And you look at this, and actually this one sort of stares out at me for some reason. I mean, that 49 is basically 50, which happens to be double 25. And I see this 144. If I double it, I get 288. That's one off. Ooh, double 841. That's 1642. I got 1681. That's one off. Double 4900 is 9800. We got 9801. We're one off. It looks like these numerators are always the doubles of the denominators, but always one off. Double 25, 50, one off. Double 4 is 8, one off. Double 1 is 2, that's one off. That's one off. Everything's one off. In fact, this one is actually 1 too high. I wanted 8, I got 1 too high. This one is 1 too low, I wanted 50, I got 1 too low. This one's 1 too high, I wanted 288, 1 too high. I wanted 1642, that's too low. So it looks like it's both high and low. So it looks like the numerator squared compared to double the denominator squareds are basically the same, so we're always off by 1, either 1 too high or 1 too low. It looks like we got this structure going on. Looks like that's what's going on here. All right, so let me see if I can prove that's true. We certainly proved that's true for this much of the ladder. We went up to that one. This relationship is definitely holding for each fraction up to there. So maybe what I need to do to prove it's true for every fraction of the ladder, as I suspect it is argue as follows. If we know this relationship is true for one fraction of the ladder, here's one fraction of the ladder, we know this is definitely holding that the numerator squared minus double the denominator squared is basically the same, but just off by 1. If we know that's true for one ladder, if we can prove one fraction in the ladder, if we can prove that, then logically follows that it must also hold true for the next fraction in the ladder, then it must hold for every fraction in the ladder. So I know it's true for this one, and if I can prove it's true for one, it must be true for the next, then it's true for the next as well. Now I know it's true here, and I've proved that it's true for one, it's true for the next, then it's true for that one as well. I can just march my way along the ladder and see it must be true for every single fraction in the ladder. So let's see. If I know the relation is true for one number, can I prove that the relationship is actually true for the next fraction in the ladder as well? That is this sort of thing happening for this next fraction in the ladder? Which means I need to see what is this relationship saying for that fraction. Well, it's the numerator squared, but my numerator is now new and different. This is the new numerator, squared, minus double the denominator squared. My denominator is now different. It's now minus double this denominator squared. And I'm hoping that this is still plus or minus 1. Is it? Is it? Okay, well, let's see. So, it feels very natural to want to expand these things that are being squared. So I get a squared plus 4b squared plus 2b plus 4ab minus twice a squared minus twice a squared minus twice b squared and 2ab minus 4ab. All right, let's cancel those 4ab's cancel. I'm getting 4b squared take away 2b squared. I'm getting 2b squareds, a squared minus 2a squared. I get minus a squared, and the rest is that. Oh, which is the exact opposite of what I just know is what I've got up here. The relationship I know is true. So I'm getting the opposite of plus or minus 1. I'm getting minus or plus 1. Yes, for the next fraction, that relationship is again off by 1, but if it was 1 over before, it's now 1 below. If it was 1 below before, it's now 1 over, which I think is what we saw. This was over, next one was under. This one's under, next one was over. This one was over, the next one was under, and so on and so on. So it does alternate being 1 over and 1 under as we go along. Beautiful, okay. So I think we've now established this relationship is indeed holding for every fraction that appears in Theon's ladder. Brilliant and gorgeous. In fact, I really like that because that now actually establishes Theon's claim. I bet we can now prove that these fractions really are converging to the square root of 2. Here goes. Because we know each fraction satisfies a squared minus twice b squared is plus or minus 1. Let me divide throughout by b squared. So a squared over b squared minus 2 is plus or minus 1 over b squared. All right, so this is saying a over b squared is 2 plus or minus some extra stuff. A little bit of error. In fact, what are the denominators doing? The denominators are always getting bigger. We started with the number 1 and we kept adding 1s and other things to it. As we started 1 and 1, we got to 2. We're always adding integers together, positive integers together. These numerators are indeed growing. These values of b are getting bigger and bigger and bigger as we go along the ladder. That means, 1 over b squared is going closer and closer to 0. This is actually converging to 0, which means a over b, these fractions are getting closer and closer to 2 as we go along the ladder. Or if you like, let's take the square roots of everything. That means the fractions themselves are approaching the square root of 2 as we go along the ladder. Indeed, Theon's ladder is actually converging to a fraction. It gives a sequence of fractions that converge to the square root of 2, giving better and better approximations indeed. Whoa! So there is our first piece of structure, which actually seems to be the key of explaining why the ladder works. And now I have an extra challenge for you. If you want to really Okay, here's a challenge question for you. Can you prove that if one fraction in Theon's ladder is off from the square root of 2 by some error, that the next fraction is going to be off from the square root of 2 by less than a quarter of that error? That we're always reducing the error from the square root of 2 by a factor of 4 as we move along the ladder? We are really converging to the square root of 2. Can you establish that? There's a lovely geometric interpretation to Theon's process. It goes as follows. Start by drawing a little square. I'll call it a 1 by 1 by 1 square. 1, 1, 1, 1. Great. But think of it as a rectangle with a long side and a short side. I guess a long side of 1 and a short side of 1. So the long to short ratio in this rectangle is 1 over 1. Now, do the following. Add a square to the short side, 1 by 1, 1, 1. Add a square to the new long side, which I now guess is 2 by 2 by 2 by 2. That gives me a new, bigger rectangle with a long side of 3 and a short side of 2. Long to short ratio of 3 to 2. Now do it again. Add a square to the short side. That's be 2 by 2 by 2. And then a square to the new long side, which must be 2, 2, 1. That's 5, 5, 5, 5. And now get a new rectangle with a long side of 7, long side of 7 to a short side of 5. 7 over 5. And you start to see the fractions in Theon's ladder appear. If you do it one more time, add a square to the short side and to the long side, you'll get 17 over 12 as the long to short ratio. Whoa, whoa. Why? What's going on there? Let me do it generally. Suppose I've got a rectangle given by the ratio A over B. I want a long to short ratio A over B. Here it is, A to B. So long side is A, short side B. The process was add a square to the short side, I guess that's the B, so I get a B, 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 B there, and then add a square to the new long side, which is, how wide is it? That's a B plus A, so it's A plus B wide, A plus B, A plus B, A plus B. So we've gone from that to a new rectangle with long to short ratio. Well, that's A plus B, and this is A plus B plus some more, so this is A plus B plus an extra B. Long side is A plus 2 B's on a short side of A plus B. Yes, that's precisely Theon's construct. Beautiful, beautiful. In fact, you'd argue, if I go back to the very beginning, draw a little 1 by 1 square and just go for this as long as your heart contents. Draw square on the short side, square on the long side. Add a square to the short side, add a square to the long side. Add a square to the short side, add a square to the long side. Add a square to the short side up there, add a square to the long side. Do it for 1,000 times in a row to get a picture you're happy with. You will get a rectangle with proportions, long to short ratio, somewhere along Theon's ladder. You know it's going to be a rectangle with proportions very close to the square root of 2. A rectangle with sides close to the square root of 2 ratio. Whoa, kind of fun. In fact, if you ever study something called continued fractions, you might see in those books diagrams just like that, because actually what we're doing now is a visual representation of the continued fraction expansion of the square root of 2. What does that mean? What does that mean? What did I just say? All right, here's what's going on. Let me give a little crash course in continued fractions, at least for this particular context. Let me play with what's going on here. Let's tease that apart a bit more. So we're saying you start with some number, a over b, a fraction, and you replace it with this. That's a plus b plus an extra b. Well, a plus b over a plus b is 1 plus an extra b over a plus b. So I'm really doing that. But let me now see if I can make this look more like what I started with. Let me divide the top and bottom here, each by b. That won't change the fraction. So I'm saying this is really 1 plus divide by b, divide by b, divide by b. But let me write this out 1 plus a over b. Does that make sense? Do you see what I did there? So I'm really saying here is, okay, I did that. If you start with some fraction a over b, you're doing 1 plus 1 over 1 plus what you just started with. So what the process really is here, you're starting with some number called x, and what you're really doing is replace it with 1 plus 1 over 1 plus x. That's what's really going on in Theon's construct, at least algebraically, and actually even geometrically, using those rectangles ideas. Great. But then see what happens here. What's going on in Theon's ladder if I think of it as this way? Well, we start with the fraction 1, 1 over 1, 1.0, the very bad approximation of the square root of 2, and the process says, please replace that by 1 plus 1 over 1 plus what you started with, which is 1. That's really what? 1 plus 1 plus 1 over 2. Yes, that really is 3 halves, 1.5. Great. But then keep going. Replace what you've got with 1 plus 1 over 1 plus what you've got. Okay, so I'm going to replace this is what I got with 1 plus 1 over 1 plus what I've got, 1 plus a half. Which is really 1 plus 1 over 1 plus 1 is 2 plus 1 over 2. Let's leave it like that. I won't simplify it anymore. But if you unravel it, it is 7/5. I promise you it's 7/5. Then do it again. Replace what you've got with 1 plus 1 over 1 plus what you've got. All right, so do it again. 1 plus 1 over 1 plus what I've got. What I've got is 1 plus this. So it's 1 plus 1 plus, oh, let me write 2 right there. 2 plus 1 over 2 plus 1 over 2. Oh, do you start to see like this sort of like tower or downward tower going of all these 2's? Because if I do it again, oh golly gee, do it again, what do I get? Take what you've got and replace it with 1 plus 1 over 1 plus what you've got. Well, 1 plus that gives me another 2 there, plus 1 over 2, plus 1 over 2, plus 1 over 2, plus 1 over 2. Did I do enough there? Whoa. It looks like we're going on this infinite descent of all these 2's going down and down and down. We know this wants to become the square root of 2. We know that converges to the square root of 2. I shouldn't say that, it goes dot, 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 dot to the square root of 2. People will say, oh, here's the continued fraction of square root of 2. This thing wants to become 1 plus 1 over 2, plus 1 over 2, plus 1 over 2, plus 1 over 2, forever. We know that converges to the answer square root of 2, given what I did earlier on today. This is what people call the continued fraction expansion of the square root of 2. And you can represent it geometrically, each approximation, by squares stacked together in that beautiful way to make rectangles with sides in the ratios given by these particular fractions if you stop anywhere to find that spot. Whoa, so much maths coming together. Wow. But that's only the beginning. The people who thought about international standards for paper sizes actually thought long and hard about this issue. For example, they said, okay, let's take some standard paper. It would be very nice if it followed two fundamental principles. One is of dimensions that are like pleasing and pleasant to handle. You don't want paper that's too unwieldy in everyday life or too small in everyday life. You want some sort of nice sized paper to work with that's often a rectangle that's kind of pleasing to the eye. Okay, principle number one, be pleasing. A pleasing rectangle for paper, please. And principle number two, they said, is wouldn't it be nice if the paper we work with in everyday life is a rectangle such that if you were to fold it in half, like everyone does, it happens very often, you get a new rectangle, if I turn it 90 degrees, that's actually similar to the original rectangle, has the same long to short proportions as the original rectangle did. Long to short, same long to short ratio. I want similar rectangles. Wouldn't that be lovely? So given those two principles, they said, okay, what size paper could we offer the world that's going to be pleasing and have that nice folding property? So what needs to be true here? Well, for the folding property, they said, okay, we want some rectangle with side lengths A and B, long A, long B, such the proportions A to B are matched if you fold the paper in half. Take this paper and fold it in half along the long side, you get a new piece of paper like this. There'll be half of A that way, B this way. This is now the new long side, that's the new short side. I want the same proportions, long to short, to be the same as what I started with. I want two similar rectangles. Okay, great. So what needs to be true about A and B for that to hold? Okay, let's make this a little bit easier to unravel. Let's double that and double that. Doesn't change things. So I get 2B over A. Let's multiply both sides by A. So I get A squared over B is 2B. I was going to say let's multiply by B on both sides, but don't. Let's divide both sides by B. That tells me I want A squared over B squared to be 2. That is, I want the proportion A over B to be the square root of 2. So for a piece of paper to have the property that folding in half along the long side gives you a similar rectangle, it needs to be a rectangle in proportions of square root of 2. A over B has to be the square root of 2 for that to work. Now, unfortunately, it's very hard to manufacture items that are exactly a rational number millimeters long. Very hard. So can we at least approximate that? And people said, yes, we can. They set the A4 paper, the most commonly used paper in the A series, to be that of dimensions 210 millimeters by 297 millimeters. And you say, okay, these numbers, where do they come from? Well, first of all, it gives you a size of paper that's actually nice to handle. That's good, so first principle is fine. But does it have the folding principle? Does it have the property that A over B is root 2? Well, look at it. Look at those numbers, 297 and 210. A over B is 297 over 210. The thing to notice here is that 297 is triple 99, and 210 is triple 70. So this is really the ratio 99 over 70, which is one of the fractions in Theons Ladder. That's a really good approximation to the square root of 2. So this is it. This is a very good compromise. So there in international paper, the A4 series, we have rectangles here, 210 millimeters by 297 millimeters that are pleasing to handle and have the property that when you fold them, you stay with the same shaped rectangle. Beautiful, gorgeous, there it is. Except, I'm standing in the US right now and the paper I'm showing you is not actually following those dimensions. In the US, they don't quite follow this. If you look at this, 210 millimeters, I think it's 8 1/4 inches. And 297 millimeters turns out to be 11 3/4 inches. In the US, they don't go by paper of that size. They go by 8 1/2 inches by 11 inches instead. So A4 paper in the US, I don't know if it's called A4 actually, is slightly off. Doesn't quite have that lovely folding property in half. Okay, cool stuff though. It's kind of neat to know about all these things. Okay, now we're ready for some true magic, some mind-blowing magic. So here's Theon's Ladder. 1 over 1, 3 over 2, 7 over 5, 17 over 12, and so on and so on and so on. Beautiful. Now let's look at the terms in odd positions. 1 over 1 and 7 over 5, the first position, the third position, the fifth position, the seventh position, and so on and so on and so on. There's actually something magical about those particular fractions. In fact, let's rewrite 1 over 1 as 1 plus 0 over 1. We write this one as 3 plus 4 over 5. We write this one as 20 plus 21 over 29. Do you see what I'm doing? I'm trying to split the numerator as best I can into 2 equal parts, but it's an odd number, so I can't quite do it. 20 and 20 makes me 40. I have to do 20 and 21 to make me 41. This is basically 240. I want to do 120 basically, but I can't. I have to do 119 and 120 and make that over 169. So split the numerators apart as best you can into 2 equal parts, and then look at this. 1 squared plus 0 squared is 1 squared. 3 squared plus 4 squared is 5 squared. Check me. 20 squared plus 21 squared is 29 squared. 119 squared plus 120 squared really is 169 squared. Really check me on that one. Keep going. Check a few more terms. You are getting Pythagorean triples with the legs that differ by 1. Whoa, whoa. So hidden within Theon's Ladder, at least amongst the odd positions terms, are Pythagorean triples with legs that differ by 1. So why is that? What's going on? How could I establish that? How could I see that? Okay, so what's the structure going on? Remember, we do know that the basic structure here is that the numerator squared want to be the double the denominator squared, but they're always off by 1. Off by 1. For example, this 49 is off by 1 from double 25. And this 1681, is that what it was? Is off by 1 from this double 841. Okay. In fact, actually, we knew it was going to be under 1 over 1, under 1 over 1, under 1 over 1, alternating. This was under 1 over 1, under 1 over 1, under 1 over 1, under 1, and so on. So actually, in the odd position terms, we know we've got this relationship. They're always under by 1. 49 is double 50, double 25, but we're under by 1. There it is. So actually, these terms that I've circled here on Theon's Ladder right now satisfy that equation. Okay, so I was saying, okay, I've got one of these fractions, a over b, and what was I doing? I was splitting up the numerator into 2 equal parts as best I can. Now, you should double check, can you prove that the numerators are always going to be odd in this relationship? Well, I bet the answer is yes, because look, actually it's right here. A squared must be 2b squared minus 1. That's sure to be an odd number no matter what. Something squared is odd. Well, a itself can't be even, because even squared is even. A itself must be odd. So we know we're always dealing with odd numbers on the top. That's why I can't split them evenly. But the best I could do to split them was a minus 1 over 2 and a plus 1 over 2 and keep the b's the same. Is that right? Do they add up to a? Is that the numerator is a? You bet. A over 2 minus a half plus a over 2 plus a half. The halves cancel. That really is a over b. So I was rewriting our fraction a over b like this. Well, I split the numerator as best I could in half, and then I claimed that we must have the relation a minus 1 over 2 squared plus a plus 1 over 2 squared equals b squared. I claimed this was holding. And do you know what? It's just a matter of algebra, because this and these equations are actually identical. Expand this out, it's really saying this in disguise. Or if you like, you take that and rewrite it and show it's really saying that in disguise. They're equivalent equations. So actually, because we've got this structure going on in the odd position terms, we really do have these Pythagorean triples with legs that differ by 1. Whoa, whoa. Okay, here's the challenge. Prove that Theon's ladder actually gives you every possible Pythagorean triple with legs that differ by 1. This doesn't miss any. This is it. All the Pythagorean triples with legs that differ by 1 actually appear in the ladder. That's kind of fun to think about. Okay, now we come to my favorite, most mind-blowing part about Theon's Ladder. It's looking at every term in an even position. 3 over 2, 17 over 12, 19 over 70, and so forth. 2nd, 4th, 6th, 8th, 10th, 12th, 14th positions, and so on. Great. Now, I claim there is something magical going on about these ones. The numerators are all odd, we've seen that, But I bet we can prove the denominators here are always going to be even. Remember, this denominator was the previous two terms added together. 1 plus 1 is 2. That's odd. Odd plus even means I'm going to have an odd here, but that's odd. Odd plus odd again means I'm back to even by account of the second term. Next one's going to be odd. Odd plus even is odd there, but now I'm going to do odd plus another odd means I'm going to be even. Yes, every second denominator is even. And what we do now is something strange. I'm actually going to halve the numerators and halve the denominators as best I can. Well, the denominators are even, I can halve those. But the denominators are odd, I can't really halve those, except I'm just going to ignore any extra halves that come up. For example, half of 3 is 1.5. Ignore the half, just write 1. And half of 2 is 1. Half of 17 is 8.5. Ignore the half, just write 8. Half of 12 is 6. Half of 99 is just 49. Or it should be 49.5. Ignore the half, and 35, and so on, and so on, and so on. And here's what we're going to do with these. Ones are very hard. They're kind of trivial. Let me go to 8s and 6s here. What I'm going to look at here is what I'm going to write down as the 8th triangular number. 8th triangular number. That is, I'm going to draw a triangle of dots. 8 rows. First row is 1 dot. Second row is 2 dots. Then row 3 is 3 dots. Row 4 is 4 dots. Row 5 is 5 dots. Row 6 is 6 dots. Row 7 is 7 dots. Row 8 is 8 dots. Bingo. There is the 8th triangular number. It's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 dots. I'm going to assume that we do know a way to add these things. That equals 8 times 9. The biggest number plus 1 more, all divided by 2, so that's really 36 dots. I have here 36 dots. I'm assuming we know how to sum the first n counting numbers. It's n times n plus 1 all over 2. All right, great. All right, so the 8th triangular number is 36 dots. Great, 36. Let's look at the 6th square number. I'll write it this way, 6th square number, 6 square. There'll be a 6 by 6 row of dots, array of dots. 6, 1 row 6, a second row 6, a third row 6, a fourth row 6, a fifth row 6, and a sixth row 6. Bingo, there's a very exciting picture of 36 dots. Whoa! The number 36 is both square and triangular. This has given me a number that's squangular. 36 is squangular, both square and triangular. Whoa! Now the reason why 1 isn't interesting, if I did the same thing here, it's sort of kind of trivial to draw this. What's the first triangular number? It's 1 row of 1 dot. Not very exciting. What's the first square number? It's a 1 by 1 array of dots. Not very exciting, it's 1 dot. But it's still, either way, it's 1 dot. The number 1 is both square and triangular. This is 1 is also squangular in a kind of trivial way. Not very exciting. However, 49 as a triangular number. 49 as a triangular number, it would be 49 rows. 1 plus 2 plus 3 plus 4, all up to 49 dots. So that would be, 1 plus 2 plus 3 plus all up to 49 is 49 times 50, all divided by 2. That's really 49 times 100 divided by 4. 4900 divided by 4 is 12, 12, 5. And if I look at the 35th square number, 35 times 35, guess what, is 1225. 1225 is actually squangular. Whoa, whoa. And check, if you go to the next fraction in Theons Ladder, the next term in even position, I bet it will give you the squangular number 41616. That's also squangular. So hidden within these even terms are the squangular numbers. I love it. I absolutely love it. All right, so why? Why would Theons Ladder encode squangular numbers in this way? What's going on? What's going on? Let's see if we can establish this. All right, so let's see. We do know that the basic structure behind these fractions is that numerator squared and denominator squared satisfy this relationship. A squared minus twice b squared is always off by 1. Except last time we saw these are the ones that are below 1 by 1, and these positions are the terms that are above by 1. This is plus 1. So we know that relation is going on. All right, now, what was I asking us to do? I was asking us to compare from a fraction AB, get a triangular number and a square number from them. So first of all, we took this numerator, which we knew was odd. We said basically halve it. So it'll be take it down by 1 and then halve that. We're looking at that triangular number, which we know is given by the formula n times n plus 1 all over 2. It's given by this formula, a minus 1 over 2, that's n, times a minus 1 over 2 plus 1 all over 2. There's a crazy formula for the a minus 1 over 2 triangular number. And for the denominator, we just simply halve those. So I'm comparing with the halved numbers for the square numbers, which we have a formula for. That will be b over 2 squared. And we're claiming that this triangular number is sure to equal that square number. That is, we're claiming this crazy formula equals this crazy formula, equals b squared over 4. That's not too crazy. All right. Is that true? Is that true? Okay, there's a lot of two-ness going on here. Let me multiply everything by 4. Throw out by 4. So what am I going to get? I'm going to get 2 a minus 1 over 2 times a minus 1 over 2 plus 1 equals b squared. Did I do that correctly? I think I did. Okay. A minus 1 over 2 plus 2 over 2 gives me a minus 1 plus 2 all over 2. This is really twice a minus 1 over 2, a plus 1 over 2 equals b squared. In fact, let me multiply by another 2. This is telling me 2 times 2 times all this equals 2b squared. But then a 2 will cancel here, a 2 will cancel here. It's telling me that this equation is really this equation disguised. A minus 1 times a plus 1 equals 2b squared in disguise. So these two equations, this equation here is really that equation. That is, it's really this equation in disguise. A squared minus 1 equals 2b squared. It's really this equation in disguise. Whoa, whoa. This equation here, this defining property of Theon's fractions in the even positions is precisely the equation that gives me a triangular number equaling a square number. So bingo, we have it. We absolutely have it. So all the odd positions encode Pythagorean triples with legs that differ by 1, and all the even positions encode squangular numbers. Wow, you have to love it. So here's the challenge. Here's a good challenge for you. Prove that every squangular number actually appears from this process in Theon's ladder. That this process here misses no squangular numbers. It's got each and every single one of them. And the same is true for the Pythagorean triples with legs that differ by 1. Theon's ladder contains every single one of them. Whoa, whoa, that's really good to think about. I just want to point out we're on the verge of something marvelous. I'm actually obsessed with the squangular numbers. I think they're spectacular. 1, 36, 12, 25, 41, 616, and so on and so on. The list goes on forever. And the natural question is there a formula for the numbers in the sequence? And the answer is yes. And we are right on the verge of being able to prove that the nth squangular number is given by 3 plus the square root of 8 to the nth power, minus 3 minus the square root of 8 to the nth power, all divided by twice the square root of 8, all squared. Whoa! Whoa! Put in n equals 1 into this formula and you'll get 1. Maybe that's possible to believe. Put in n equals 2 into this formula and somehow all the square roots of 8 cancel out and give you the nice whole number 36. And put n equals 3 into this formula, try it. All the square root of 8 somehow cancel out each other out to give me a nice whole number of 1225. There's a formula for the squangular numbers. It's amazing. And we are at the point we can prove this, and I'll do that as an appendix to this video. Leonard Euler in the 1700s actually derived this formula as well. It's well known. It's the formula for the squangular numbers. You've just got to love it. Okay, so here's one final challenge. So here's Theon's process, and we applied it with a starting fraction of 1 over 1, and it led to this beautiful ladder of fractions that encodes Pythagorean triples with legs that differ by 1 in the odd positions, and squangular numbers in the even positions. Amazing. Some geometry of numbers in those even position terms. Gotta love it. But actually, you don't have to start with the fraction 1 over 1. I'm wondering, if we started with a different fraction, say maybe 2 over 1, the fraction 2, we can apply this process to that as well. The denominator will be the two terms you've got added together, and the numerator will be the top term plus double the bottom term. So this will give me 2 plus 1 is 3, 2 plus double 1 is 4. Do it again, 4 plus 3 is 7, 4 plus double 3 is 10, and so on and so on. And now you have to wonder, do these odd position terms still encode Pythagorean triples? or some variation of Pythagorean triples, or maybe Pythagorean triples, the legs that differ by some other number like 2 maybe or something. There must be some geometry to the odd position terms. And the even position terms, probably not square numbers being triangular, but maybe they're oblong numbers that are triangular, or maybe square numbers that are pentagonal. Maybe there's some other geometry going on in those even position terms. What's going on? I bet there's more geometry hidden in these sorts of ladders. In fact, you can start with any sort of fraction you like, 5/3, and off you go. Maybe there's geometry hidden in those ones as well. In fact, there's a whole universe of fractions of ladders to explore here and the geometry that might be hidden within them. There's the wonder and awe of mathematics. I love it, just playing with it. So here's one starting example, but we now have an infinitude of study examples to wonder about. Wow, what wonder, what joy, what delight, what fun to explore. Okay, here's an appendix video for the mathematically brave, because I actually want to derive this formula for the nth squangular number. It's crazy, it's going to take a little bit of doing, but we'll get there, we'll do it. Remember the squangular numbers, the numbers that are both square and triangular. 1, 36, 12, 25, 41, 6, 16, and so on and so on. And we saw them with Theon's ladder. They came from the even position terms. Here they are. The idea was you take one of these even position terms, halve the numerator as best you can, like a minus 1 over 2, halve the denominator, b over 2. Turns out the a minus 1 over 2 triangular number equals the b over 2 square number. That's the relation a squared minus 2b squared equals 1 in disguise. Bingo. Which means the squaring number I'm really dealing with this square number, that's probably the easiest for me to have, is just b over 2 squared. So that's the squangular number coming out of Theon's ladder. Alright, so that means I've got to play with the denominators, of these numbers here. So let me write out the sequence of numerators, there they are, and the sequence of denominators. I call them ANs and BNs. I want to play with the BNs, at least the BNs in the even positions. Okay, let's keep that in mind. But, before I get going in something complicated, let me just recall the structure of Theon's process. The numerator before becomes the previous numerator plus twice the previous denominator, and the denominator becomes the numerator plus the previous numerator plus the previous denominator. So that's the recursion relations here. I'm saying the next numerator, n plus 1, is the previous numerator plus twice the previous denominator, and the next denominator is actually the previous numerator plus the previous denominator. So I've got these sort of intertwined recursion relations going on. So I'll try to get formulas for those to then unravel and get this formula here, which would be that formula there. Hopefully, with all these root 8s everywhere. Ooh, that's scary. That's really scary. All right, okay. I don't like these things being tangled. I wonder if I can detangle them in some sense. For example, I can see this is really an plus a bn plus another bn. The reason I did that, because an plus bn is the next bn. So it's really bn plus 1 plus bn. Oh, so the n plus 1th numerator is the n plus 1th denominator plus the previous denominator. So I could use that right here. I can say that bn plus 1 is really this formula, but it's shifted down 1, so it's bn plus bn minus 1 plus that bn. So bn plus 1 is actually twice bn plus bn minus 1. I've got that going on. Let's check. One number is twice the previous one plus the one before that. So 5 is double 2 plus 1. 12 is double 5 plus 2, yes. 29 is double 12, 24 plus 5, 29, yes, that's what's going on. I also have, just to be really clear, this starts with B1 being 1 and B2 being 2, okay. Just because 0 is a nice number to work with, I could actually put an extra number here, because this 2 is really double 1 plus nothing more. I could say putting B0 equals 0 fits nicely. In fact, it does fit nicely. That fits the pattern too. So let me just start with that. Because once I've got the first two numbers, 0 and 1, that means everything is technically following from that. I know how to get the next one. Do twice the 1 plus the 0. And then I know how to get the next one. Right, so think about recursion relations. As soon as you've got the two starting values and a recursion relation like that, you've really got all the values. All right, so that defines all the information about the sequence B. So if I can get a formula for the B's, great. But I want the even terms for every second B, that'd be great. Then I could do this, and hopefully it's that formula. All right, so I got my job. I got it figured out. I want to find the formula for the B's. All right, okay, so what do I need here? So let's get rid of that, and, well, I don't know how much room I'm going to need. Okay, here's the formula. I'll live right up here. B, n plus 1 is twice bn plus bn minus 1, with b0 being 0 and b1 equals 1. That's enough to define everything. All right, great. And I don't need that for the moment because they're already up there, and I've got that for the moment. If I need it again, hopefully I can just recall what I said. All right, okay. All right, let's do it. Let's do it. Now, if you look at the sequence of the denominators, 1, 2, 5, 12, 29, 70, and so on, probably the first thing you might want to do is start taking differences, and then difference of the differences, and the difference of the differences, and the difference of the difference of the differences. That seems a very standard thing to do, and you'll find it gets you nowhere. Turns out, this is not going to be a nice polynomial thing. You won't ever get constant differences. They'll tell you, you'll give up after a while. Say, oh, can't be polynomial. In which case, at that moment, you just do what I did, put your hands on your head and wonder, what can I do? And here's a standard thing that people have thought about. Well, if it's not polynomial, just engage in wishful thinking. What's the next best thing? I mean, wouldn't it be lovely if it's not polynomial, it was just, say, a very basic exponential series, like a geometric series like this? Wouldn't that be amazing if there's some number x such that really bn is just x to the n? I mean, I know that's ridiculously too much to hope for, but let's go with it. Let's play with it. Is there a value x that satisfies this recursion relation that could help us out? All right, well, if this is true, then I want bn plus 1. I want x to the n plus 1 to equal twice x to the n plus x to the n minus 1. Okay. Let's divide through by x to the n minus 1. They'll leave an x there and an x squared there. So it tells me x squared should equal 2x plus 1. Great. So if I've got any hope of finding an x that works, it better be something that satisfies that quadratic equation. Quadratics, I can do those. X squared minus 2x equals 1. Add a 1, 2. That's really x minus 1 squared is 2. X minus 1 is root 2 or negative root 2. So x all by itself is either 1 plus root 2 or x must be 1 minus root 2. So actually, there are two geometric series, one with x being 1 plus root 2, another with x being 1 minus root 2, that actually does fit that equation. Whoa, whoa. Let me call that one x1 and x2. So if I use x1, I know 1x1, x1 squared, x2 squared, or x1 squared, sorry, x1 cubed, x1 to the fourth actually fits that recursion relation. Bingo. If I use this one, 1, x2, x2 squared, x2 cubed, x2 to the fourth. Whoops, I missed the squared. Where's the rest? No, that's right. I did something funny there. All right, anyhow, use that as the geometric series. That also fits that recursion relation. Bingo, beautiful, that's nice. 1 plus root 2 and 1 minus root 2. But here's the amazing thing. If I did a combination of these two things that fit the recursion relation, some number times x1 to the nth plus some number times x2 to the nth, if I took that, I bet you could just shove it into this and see that bn plus 1 will have to satisfy 2 bn's plus bn minus 1 because the individual powers of x2. I bet you can combine these and see that actually, for any old constants you like, choose any constants alpha and beta you like, this too has to logically fit the same recursion relation. Just check that out. If these do, then that does as well. Wow, wow, okay. Which means then, these basic ones aren't good. They're not starting at the right place, 1, 2, 5. But maybe I can choose alpha and beta to get things to start how I want them to start. Remember, I did want oh, there it is. I want b0 to be 0 and b1 to be 1. Not happening there, but maybe I can choose constants alpha and beta so it's happening here. Oh, I'm loving this wishful thinking. All right, let's keep going. If I want b0 to be 0, that means I want 0 to equal alpha times 1 plus beta times x to the 0, 1. Oh, I need beta to be negative alpha. I need beta to be negative alpha. Oh, I love it. Okay. That saves some work here. Great. So that should be negative alpha. Great. All right, next, what am I going to do? I want b1 to be 1. I want 1 to equal alpha times x1 minus alpha times x2. All right, now I remember what x1 and x2 were. I erased them from the board. I do remember. x1 was 1 plus the square root of 2. x2 was 1 minus the square root of 2. So this is telling me I want 1 to equal alpha times 1 plus the square root of 2 minus alpha times 1 minus the square root of 2. Alpha times 1 plus root 2 alphas. That's minus alpha times 1. So the alphas are going to cancel. So I've got root 2 alpha plus another root 2 alpha. I've got 2 root 2 alphas. Oh, that's root 8 alpha. Oh, root 8. I like root 8s. That tells me alpha better be 1 over root 8. 1 over root 8. This is 1 over root 8. And this is 1 over root 8. Wow. Messy board technique, but this is speedy math for the brave. So, oh, that's it. That's exactly what. I've got some formula now that actually fits that recursion relation and starts exactly how I want it to start. It starts correctly for the first 2 numbers. This sort of recursion relations had to get one number from the previous 2. Therefore, it fits all numbers in the sequence 1, 2, 5, 12, 29, 30, 70, and so on. Beautiful. What is it? It's this. Bn is x1, 1 plus the square root of 2 to the nth power minus 1 minus the square root of 2 to the nth power all over root 8. There it is. I have a formula for the denominators. That's it. Done. Gorgeous. Amazing. Amazing. Wishful thinking worked out there. So it's kind of geometric. It's a combination of 2 geometric series. There it is. The denominators follow this formula. Put in n equals 0, out comes 0. Put in n equals, yeah, I can see it, 1 take over 1. Put in n equals 1, out comes 1. Put in n equals 2, out comes 2, I bet. Put in n equals 3, out comes 5. I bet you. I know it. In fact, I know it. I just know it without even doing the arithmetic. There it is. All right, so what do we want? We don't want every denominator. We want all the even position denominators. So actually, what I really want to focus on is b of 2n. The 2, the 12, the 70. All right, so let's put 2n instead of n in this formula. 2n, so that's really, okay, 1 plus root 2 squared to the nth power. Let's write more neatly, James. 1 plus root 2 squared to the nth power. 2n here is really 1 minus root 2 squared to the nth power, all over root 8. Okay, so I really want those terms. All right, okay, arithmetic galore. 1 plus root 2 squared, that's 1 squared is 1, plus root 2 squared is 2, plus 2 root 2. That's 3 plus 2 root 2, that's 3 plus root 8. That's 3 plus root 8. Oh, I am really loving this. This is feeling great. Just look at it. And 1 minus root 2 squared. So 1 squared is 1, plus negative root 2 squared is root 2, is 2, minus 2 root 2. 3 minus root 8. 3 minus root 8. Oh, this is amazing. All right, so our second term in the sequence of denominators is given by that formula. And what did I want for the Squangular number? It's this. The nth Squangular number is the eventh term divided by 2 all squared. So the nth Squangular number is, drum roll, is this even term divided by 2, 3 plus root 8 to the nth power minus 3 minus root 8 to the nth power over 2 root 8, there it is, and then square it, because that's actually the base of the square, part of the Squangular number, so the Squangular number itself is that number squared, which, voila, is indeed Euler's formula. Wow, wow, we did it. Okay, that's fabulous. I'm wondering actually if you want to find some sort of general formula then for all those Pythagorean triples with legs that differ by 1. Remember we had a minus 1 over 2, a plus 1 over 2, and b? I wonder if there's an analogous formula you can come up for the odd position terms that tells me something about, I don't know, all the hypotenuse that appear in the sequence of those Pythagorean triples or something like that. Can you do this work for the odd number terms as well and discover something interesting about Pythagorean triples and their general formulas? Wow! A universe of wonder and play. What can I say?